Okay, good. Yeah. Welcome to part 4. So again, the objective is data-driven stochastic optimization. Like we want to learn stochastic optimization problems given some data. What will change now is instead of offline learning, the offline learning was I give you a bunch of samples upfront. And the question was what's the minimum number of samples I need to learn up to an additive epsilon. Now we'll do so-called online learning, where in some sense you play a repeated game. Like I think of it in days. Like day one, you play an algorithm, then like you get some feedback. The algorithm was run in practice. Uh, Now day two, you have some feedback from the first day. Based on that feedback, you play another algorithm on day two, day three. So as maybe the time progresses, you are allowed to learn as you go. It's not that upfront I have given you a bunch of samples. So as you go, you can improve and use your feedback to improve your algorithm. And the objective is to perform well on average. Good. So the plan of this lecture is online learning for these stochastic problems. In particular, we'll focus on something like some kind of partial feedback. Okay, let's formalize it a little bit. So first of all, what do I mean by online learning? Uh, so as I was saying, it's a repeated game over capital T days. Remember, initially I was giving you capital T samples upfront. Now think of capital T is my time horizon, maybe 365 days of a year or something. So I want to look at the average performance of your algorithm over 365 days. Each day, you are going to play an algorithm. I'm going to call it alg-t. This is the algorithm that you play. Maybe like you're running some kind of a posted, like some revenue maximization problem. You offer some price to the bunny on the tth day. That price is what's alg-t. And a random bunny shows up from the distribution or like some random sample comes. Again, my function is between 0 to 1. The goal is again to minimize the performance, the average performance of my algorithm, or sometimes people think of this as regret, which is like T times opt minus the total performance of my algorithm. Good. Or alternatively, sometimes people divide this entire thing by 1 over capital T, which is like f of opt minus the average performance of my algorithm. So remember, like if all the samples are kind of given upfront and so on, like this is the same notion of regret as we were defining earlier. But now I want to look at the average performance of my algorithm over capital T days. Good. So something that's more subtle here is what kind of feedback do you get every round? So one is called the full feedback, where on the tth day, you play an algorithm. Then there's some freshly drawn sample, which evaluates the performance of your algorithm. This is the sample xt. But then at the end of the day, are you revealed this sample or not? So there are two versions of this model. One is the so-called full feedback model, where you are revealed the entire sample. In the other world, you are not revealed the sample, you only receive some partial feedback. Maybe to give you an example, like again, going back to the revenue maximization problem, you're trying to sell a carrot to a bunny. You offer the carrot to the bunny at some price. And then like a fresh bunny is drawn from the distribution. If the bunny's value is like, more than the price, then the carrot sells, otherwise it does not. There are two models. One model could be that at the end of the day, you learn what the value of the bunny was. Okay. And based on that, like also you learn whether the carrot was sold or not. Another world would be like you only learn whether the bunny bought the carrot or not. You never learn their true value. You only learn a partial feedback, which is whether the carrot was sold or not. Good. And this is like a general model. I mean, we'll get to it. But let's for a moment talk about the full feedback where you reveal the entire sample. Good. So there are like all these. So again, like, I guess I had written this up. Single item revenue maximization, where you're maximizing the value, which is the price offered minus the probability that the item is sold, 1 minus f of p. So you're maximizing this. On tth day, you are going to play some price, a random reward you get, which is basically the price that you offer times the indicator that the item is sold. Want to minimize the regret, which is the average revenue that you make versus like what the optimum would have done which had known the distribution. And usually you're interested in, I mean, the average regret, like because I'm doing capital T rounds, can you get sublinear in T regret? So little o of capital T. That's the kind of guarantee we'll often care about in online learning setup. In other words, if I scale it by like 1 over capital T, it's saying that the average, if I scale this by capital T, average is tending to 0. Like the average error is tending to 0. Good. Any questions about like the online learning model? So the first claim is that for full feedback problems, like where you're receiving these samples every day, I'm saying online learning and offline learning are basically the same. It doesn't matter too much, up to some constant factors, which will not constant or like log factors, which we won't care about today. So if you're receiving these samples every day, like the full sample at the end of the day, you learn whether like what was the value of the bunny that showed up, then you're fine. And the reason is simply like by doubling click. So like what's the lemma? The lemma is that if you have an offline learning problem, for a problem for which you can get like some alpha over epsilon squared sample complexity, you can get some alpha times root t regret. Okay, so if you have this epsilon is the error that we were trying to guarantee. Like in the online learning language, this epsilon squared translates to root t regret. Or in other words, like if I scale it down by 1 over t, it's like 1 over root t regret. And like root t is the right thing. I mean, this is tight. You cannot hope to do better than root t. I mean, morally, think of it like if I perform capital T coin tosses, unbiased coin, like optimum is T over 2, like number of heads. Let's say goal is to maximize number of heads. But in reality, there will be like T over 2 plus minus square root T. And that plus minus square root T, nobody can guess or anything optimize over it. So in some sense, root T you have to pay everywhere. And that root T in the other language is this 1 over epsilon squared. That's the reason like why 1 over epsilon squared was usually the right answer for all our previous offline learning problems. And the claim is that any offline learning algorithm can be applied for the online learning problem as well. And the simple trick is just by the doubling trick, as it's often called. Basically, for the first I days, like you run some algorithm, you receive the feedback. Now you have I sample, like whatever, 2 to the I samples. Send it to the offline learning algorithm, first 2 to the I samples. It returns you some algorithm. Run it for the next 2 to the I rounds. Like now, in some sense, you have 2 to the I plus 1 samples, run it again, send it again to the offline learning algorithm. Whatever you get, run that for the next 2 to the I plus 1 rounds and continue in this way. So you can argue like this will work fine. It will, naively, it will lose like log capital T, kind of like you will lose a log factor. You can do a more careful analysis. You don't even lose a log factor, only like a constant factor. Good. So the main takeaway here was that like, okay, let's say going back to, we just saw in the last lecture that how we can get something like n over epsilon square sample complexity for all these stochastic monotone problems. So for offline learning, we can get something like n over epsilon squared sample complexity. That basically translates to something like, did I mess up something? Maybe it's like, I think I messed up. Like it's n times root t, not square root n square root t. I think it will be n times square root t regret for all of these problems. Yeah, so this, yeah, n should have been outside the square root. But that's an immediate corollary. Does this make sense? Let's take maybe a question. Okay, so long story short, offline learning and online learning are equivalent. If in online learning, you're getting full feedback, you're getting to see all these samples exactly after every time step, then in some sense, you can pretty much applying this doubling trick, you can get it. It's as good as if you're doing offline learning. So what's funny is, so like the focus of this lecture is going to be online learning, but with partial feedback. So what do I mean? Again, like online learning, as we were saying, each day, tth day, I'm going to play some algorithm T. I'm going to evaluate its performance on a random sample. You want to minimize some regret. And what's changing here is now you're going to receive some kind of a partial feedback. Okay, so I'm not going to see the sample. I'm going to get only some partial information, maybe whether the carrot was sold today or not, or some other kind of information. Good. So like Yeah, so basically in this revenue maximization example, I only get to see this indicator at the end of every round, whether the value today was more than the price that I offered. So whether the carrot was sold or not. If the value was above, I don't know by how much it was above. Like I offered the carrot at like price $0.5, it got sold. I don't know whether it was valuated at like $1 by the bunny or at like zero point 0.5 plus epsilon value. It's unclear. So that's the so-called, you can say, online learning with partial feedback. That's what I mean. And for many, many stochastic problems, you only receive some kind of partial feedback. That's the motivation behind studying these problems. Okay, good. So let me clarify now a bit more on this partial feedback. So usually it's differentiated between two things. Uh, it's also called, this partial feedback is also called like some kind of bandit feedback. Some historical reasons why it's called bandit feedback. Uh, so there are two versions of this. One is kind of, you can call it fully bandit or just bandit feedback. One is semi-bandit. So for instance, in some of these problems, so in the case of revenue maximization example that we are seeing, both the models will basically be the same. But when you are working with high dimensional distribution, let's say I'm talking about some optimal stopping problem. So what's like the optimal stopping problem? You have these random variables. You open the first random variable, you get to see its realization, the profit inequality problem. You have to immediately say accept it or reject it. Now I go to the second random variable. I again accept it or reject it. Third random variable, I accept it or reject it. Let's say I accept the third random variable. Now, there are two versions I could define of this problem. One is in the bandit feedback, I get to see only the realization of the third random variable that I accepted. A semi-bandit would mean like I get to see the realization of the first three random variables, but random variables 4 to n, like all the random variables that I did not even open, I never get to see them. So both of them are some kind of partial feedback because I'm not getting to see the entire n samples, like n random variables. I'm not getting one sample from all the n distributions. In one case, I'm just getting the third random variable, the one where I stopped. In another case, I'm getting the first three, the ones that I opened. So when I'm getting the first three, that's what I'm going to call something like a semi-bandit feedback, which is somewhere in between like full feedback and like fully bandit feedback. And bandit feedback is where you just get to see the reward. Good. So maybe let me clarify this again via the table. So there are like different axes. So the y-axis is like the bandit, semi-bandit, and the full feedback. In full feedback, you get to see everything basically. So reward means the performance of your algorithm, how much reward it gets. So in all the three models, you're going to get to see the reward. Like whichever random variable you accepted in the optimal stopping problem, maybe I took the third random variable, then I get to see the third random variable's value. Probed random variables or opened random variables, by that I mean the random variables which you saw. So in the optimal stopping problem, I saw the first three, like some prefix of the random variables I'm going to see. So I'm going to see all their realization. In Pandora's box, what would it mean? Something like I'm opening these boxes one by one by paying costs. So whichever boxes I open to pay by paying some cost, I get to see their realizations. The ones I don't open, I never get to see any realization. So that's my semi-bandit feedback there. So in all the cases, yeah, so that's like the two extreme. In bandit feedback, you just get to see the reward and nothing else. In full feedback, you get to see everything. And semi-bandit is like somewhere in between. I'm going to define this a bit more formally later, but I wanted to give the intuition. Like that, as soon as we talk about partial feedback, and partial feedback usually only makes sense in the online setting, so online learning setting. There are two regimes. One is bandit and semi-bandit. And yeah, of course, like our life and in designing an algorithm becomes much more difficult if it's bandit feedback. Semi-bandit is, yeah, relatively easier because at least you get to see a few more than one single random variable. Question?
You don't even get to see where you stop.
Exactly. Like, yeah. So in a priori, you may not even get to see, like in an optimal stopping problem. So I'm saying, although you get to see the third random variable's value, like in the optimal stopping problem where you stopped, maybe you don't even get to see whether it's the third random variable or maybe the first random variable took already the value. So you don't even get to see the stopping index. So you can, yeah, it can be like really complicated, the fully banded model. And yeah, in reality, like there's like a whole spectrum of feedback. And yeah, again, our objective is to come up with, let's say, general techniques that apply to large class of stochastic problems, uh, how to learn them. Good. Okay. So the plan for the rest of the talk is like, I guess I'll first talk about some banded feedback results and then some semi-banded feedback results. Oh, okay. This is some typo. Okay. Uh, good. So again, what do I mean by online learning with banded feedback? Now let me define banded feedback very formally. So again, each round, I'm going to play some algorithm T. Uh, the reward we receive is alg's performance on a freshly drawn sample from the underlying distribution, x1 to xt. The goal is to minimize regret. And the objective is, can we get sublinear regret? The only, okay. So the only feedback that we are receiving, yeah, okay, it's written here. Like, so the only feedback is the reward, the value of this function on the sample. I don't get to see anything else. So I don't get to see any of the xi's even. I mean, okay, if my reward is given by one of the xi's, then in some sense I get to see that xi. But the only feedback that my algorithm is receiving is the value of your function. So suppose like I go back to Pandora's box problem. I run an algorithm. An algorithm would be of the kind that maybe I'm going to open these boxes in this sequence. And at some point, if my value is like large, then I'm going to stop. Then the only thing you get to see is basically what's your total reward, which is the place where you stopped minus the total costs of inspection. That's the only feedback you get. You don't get to see any realization of any other individual random variable. But of course, there are things you could potentially infer from the information that you receive, but that's up to you, what all you want to infer. Good. And like, okay, again, like maybe connecting it back to other literature and like multi-arm bandits. So you cannot apply standard machineries on multi-arm bandits. There's like a lot of work on multi-arm bandits, like this bandit learning for general reinforcement learning or learning general MDPs. Usually those bounds don't apply because those algorithms usually have dependency either polynomially in the number of states of your MDP or like the number of algorithms. So in our case, both the number of states and the number of candidate algorithms, they're usually exponential. So those generic techniques don't apply, like for general MDP learning. Okay, good. So the result I want to, I guess, first general result I want to claim is that uh, you can get at least some sublinear regret bounds for a large class of stochastic problems. So you won't get square root t regret bounds, like, or the square root t is, remind to recall, it's equivalent to basically the 1 over epsilon squared kind of guarantees in offline learning. So you cannot get square root t regret bounds, but for a large class of stochastic problems, you can get something like t to the 2/3 regret you can get by a simple reduction. So let's say the assumption I'm making, so this is like a general trick, like that's good to know if you've not seen online learning before. It basically says that I'm going to somehow reduce my banded feedback problem. So although I'm receiving like just banded feedback to the full feedback problem. Like somehow I want to reduce my online learning with partial feedback problem to the full feedback problem. Okay, and this is not possible for every problem. So this is possible as long as you have, so that's why I'm going to make one assumption. So suppose you're like, remember our algorithm was playing different policies, like there are different potential algorithms we could play. So suppose one of our algorithms allows to, like one of the actions allows us to get an unbiased sample from some ith distribution. Okay, what do I mean by this? Like, let's say the optimal stopping problem where you're taking these random variables. On any day, I have an option of getting a sample from just the ith random variable. What would I do? I'll play basically infinite threshold for all like first I minus 1 random variables and a 0 threshold for the ith random variable. If I play this algorithm on a day, I definitely know I'm going to get an unbiased sample from the ith distribution because I've not accepted anybody else. I've just accepted directly the ith random variable. So I'm going to get an unbiased sample from this ith distribution. Similarly, for Pandora's box, you can get an unbiased sample from any particular distribution by saying that, okay, irrespective of what happens, I'm just going to take the ith random variable. Then the reward that I get in that round on that day is basically the value of that random variable minus the cost of that random variable of in Pandora's box. So for any stochastic problems where you have such an operation allowed, that is like a dumb algorithm, which allows you to get an unbiased sample from any particular distribution, a single random variable that you want. Of course, its performance will be very bad. Like on that round, your algorithm is going to basically incur as one regret because it could be very bad compared to the optimum policy. So as long as this dumb operation is allowed, the claim is you can immediately get a t to the 2/3 regret. Good. So what I mean is like, yeah. So for each I, as long as the assumption I'm making is if you have a stochastic problem where you can get an IID, like unbiased random variable, like sample from this I distribution. So this is not true for every problem. For instance, like the revenue maximization problem, where I was trying to sell the carrot. I mean, there I cannot get an unbiased estimate. Like I cannot get a sample from the distribution of the money. So it's not true for every problem, but for a large class of problems, this is true. Like for Pandora's box, optimal shopping, and many others, this is assumption is true. So if this is true, then you can just do the simple trick. So like the claim I'm saying is that under this assumption, if you have a stochastic problem that you can get like in the full feedback, you can get like root t regret for any such problem. Then you can get a t to the 2/3 regret even for banded feedback. Okay, and does anybody want to maybe speak out? Like, I mean, how would I achieve this? I'm saying there's like nothing clever I'm doing. Okay.
Yeah, it seems like you should just try to learn all the distributions of
Precisely.
the and then
Yeah. So yeah, as was suggested, like yeah, the idea is basically okay. Uh, so this root t regret in some sense that's basically saying like for the offline learning problem, I have a like a 1/epsilon squared kind of a guarantee. So basically this is saying like as long as I have sufficiently many samples from each distribution, then I'm in a good shape. We know how to solve this stochastic problem. Uh, as long as I have sufficiently many samples from each of the distributions. And in this case, we have this operation allowed that allows me to get an unbiased sample from any distribution. So what you'll do is like the simple trick, there's that in each round. So what I'll basically do is like I'm going to, on some rounds, I'm just going to, as they call it, explore versus exploit. On some rounds, I'm going to explore, which is that I'm going to choose one of the n distributions at random, and I'm just going to get like an unbiased sample from the ith distribution. So some days I will just try to explore, which is like trying to get a better estimate of the distribution. On the other days, I'm going to exploit, which is like based on the days I have like explored in the past, I have some estimates of the distributions. So whatever estimates of the distribution I have, I'm just going to run my algorithm based on those estimates. So gradually as time progresses, the number of explored rounds will increase. So I'm developing better and better estimate of my underlying distributions. So this is generally called the exploration versus exploitation trick. Yeah, you basically you just have to optimize the parameter. Like what you'll end up doing is like with some 1 minus delta probability, I'm going to like exploit, and with some delta probability, I'm going to explore. So with delta probability, in this particular case, yeah, I mean, I forget like what's the chosen value of delta, but like with some delta probability, I'm going to play one of the n random variables at random, just going to get an unbiased sample. So in some sense, in every round, I have delta over n chance of getting an unbiased sample from the any particular distribution. So yeah, so I guess yeah, so delta will basically be I think 1 over t to the 1/3 in this particular case. Yeah, again, the details are not important. So that simple idea is the following: that yeah, with some probability, with some delta probability, you choose one of the play one of the random variables at random. So as you have at least 1 over n chance of receiving an unbiased sample from any ith distribution, like delta over n. And then after you do this like sufficiently many times, like as t increases, you would have received many samples from every distribution. So then you kind of have a very good estimate, and then you can run your offline learning algorithm. All good? Yeah. So, and I mean, an immediate corollary of this would be something like for all our optimal shopping, Pandora's box, like many of these problems. you can immediately get like some t to the 2/3 regret with full banded feedback, like no extra other assumption. You can immediately get this t to the 2/3 regret because we can combine this trick with the sample complexity result that we were just saw in the last lecture. This n over epsilon squared for strongly monotone problems. Question? Yeah.
The 2/3, is that supposed to be on T or is it on all of it?
Good question. I think, okay, like maybe it doesn't follow immediately from this. I think you can maybe even get n to the 2/3. You can do like a slightly better balancing. I'm not 100%. You might be correct. Like, yeah. So yeah, I'm very sloppy here, dependency on n. But yeah, I agree. Like yeah, but the more crucial point I'm focusing on is the dependency on t. So yeah, I'm not 100% if I have the dependency on n correct or not. But then you may ask the question like, okay, for these problems, like Pandora's box, optimal shopping, or like many of these other problems, is t to the 2/3 tight, or can you do anything better? Uh, Turns out, in general, this is tight. In general, you cannot do better than t to the 2/3, but for specific problems, you can. So like this is like something, again, we had some result in Soda last year. Like turns out for optimal stopping and Pandora's box, for both of these problems, you can get some square root t bound, square root t even for fully banded feedback. There's some poly n factor. I forget, like n to the 4, n to the 6, like some factor. We did not optimize it too well. But the focus was more on the square root t. So it turns out for, yeah, specific stochastic problems, you can do better. But in general, it's not possible. So for using like by exploiting problem specific techniques, you can do better. And this is also the reason why I'm not going to get into this result or the proof of this result, because yeah, I want to focus more on general techniques in today's lecture. Yeah. So similarly, like there's also something for revenue maximization problem, like even like the bunny problem, the carrot selling problem. Turns out there also you can get some guarantees. So by the way, like for the carrot selling problem, because you cannot get an unbiased sample from the underlying distribution, even the t to the 2/3 from last slide does not apply. But turns out using some other alternate tricks, you can get like t to the 2/3 in general. And there's something called regular distribution. It's a large class of distribution that contains like exponential distributions and many others. You can get even square root t. Yeah, so, but I'm not going to get into those details because these are something like somewhat very problem specific techniques rather than like being general techniques that are applicable to many, many stochastic problems. So one open question in this direction is coming up with a better understanding or coming up with a general technique that gets you something better than t to the 2/3 for a large class of stochastic problems with banded feedback. And currently we don't have a very good understanding of this. Any questions? Okay, so yeah, the last 10-ish minutes I'll maybe spend on semi-banded feedback. Good. So what's the semi-banded feedback? As I was saying, like each round, again, online learning, you play some alg t, you get some reward, like on a freshly drawn sample. So the reward is going to be revealed to you. You're also going to get some feedback of some of the random variables that you opened. Like in the optimal stopping problem, like the first, if you stop at the ith random variable, then you get to see the realization of the first I random variables. In something like Pandora's box, the ones that you opened. So we'll formalize this in a second. What does that mean? And your goal is to minimize the regret. And can we get a priori like sublinear? So sublinear we can get because we can get sublinear already for even like banded feedback. So now how do I formally define opened or probed? So this is again going back to what we saw in the first lecture, the decision tree. So recall how we defined the stochastic optimization problem. In general, the stochastic optimization problem is you have n random variables and distributions and some constraints, and you want to maximize, minimize your objective function. For many of these stochastic problems, in general, it's an arbitrary decision tree or an MDP. But now focus on a class of stochastic problems where you have additional properties on this decision tree. So what is a stochastic problem? Like even if I know the distribution, an algorithm is going to be of the kind. In general, it could be like it's in some state, it performs some action, goes into a different state, it performs another action, goes to another different state, and you're trying to come up with an algorithm or policy that maximize the value in expectation. here we are going to look at a specific class of stochastic problems where each node corresponds to a single random variable. So problems like Pandora's box, optimal stopping, like or variants of optimal stopping and stochastic probing, the decision tree should be thought of as at the root represents a random variable. Like maybe I'm going to first perform something with the fifth random variable. So I'm going to see x5. Depending on the realization of this first random variable, I'm going to either go to like maybe x, like distribution 2, distribution 3, or distribution 7. So imagine stochastic problems where the decision trees, the nodes of the decision tree corresponds to unique random variables. So such stochastic problems is what we want to study. So like this captures many stochastic problems. So like the properties are like each node represents a unique random variable. Every root leaf path is first of all feasible for your constraints, like whatever constraints you have. And no random variable appears twice on your root leaf path, because in some sense you cannot get like two realizations of the same random variable for your stochastic problem. And this captures many problems, as I'm saying, like such as stochastic probing. You can also capture problems like submodular cover and many others, stochastic matching problems. So in many of these problems, the optimal policy looks like the following: like you get to see the realization of a random variable, then move to another random variable, then move to another random variable. So any stochastic problem where the optimal policy looks like some kind of a decision tree where the nodes represent random variables is what we are studying. And then for such a problem, semi-banded feedback, like your algorithm is going to basically take some root leaf path of this decision tree. And the semi-banded feedback would basically mean I'm going to get to see the realization of all the random variables along this path. So that's what semi-banded feedback would mean. Like, so for Pandora's box or these problems, these random variables corresponded to the boxes that you opened. So whenever you take any trajectory, the random variables that you opened are the feedback you get is precisely the random variables that you open. So for such semi-banded feedback problems, the question is that, yeah, can we come up with a general technique? And there was and I guess, yeah, so this we already know, like the monotonicity definitions. But so the claim was that there was a result from Fox last year that showed that for the large class of weakly monotone problems, so weakly monotone, so you don't even need strong monotonicity, just like weakly monotone stochastic problems under semi-banded feedback, but with discrete support. So I mean, at least this main result, this does not apply for continuous support. For discrete support, you can get some nk square root t, some square root t regret bounds with semi-banded feedback. Okay, so like the main takeaway here is that you can get even square root t regret bounds rather than t to the 2/3, which we were getting for banded feedback. So here we can get square root t even, but it's not, okay, I need like some assumption on this support size. But the point is we cannot use algorithms from lecture 3, from the last lecture, because we have semi-banded. We are not receiving full samples. We are only receiving partial feedback. Is the result making sense? Maybe a question? Yeah, and the proof is actually not that complicated, proof and the algorithm. So maybe ask a question like, so how many of you have seen UCB, upper confidence bounds, like for multi-arm bandits and all? Okay, so if you've not seen, so maybe, yeah, that's a problem on one of the exercises as well. So basically like proving it. So the classical setup is just the following. So here's like maybe a toy problem, a bit different from this. So the toy problem is the following. I place, let's say, n coins on the table. Okay, each coin has some unknown bias. So it's not like a 50-50 coin. It has some unknown probabilities. And I give you like 1,000 attempts. I've placed maybe 10 coins in front. Your goal is to maximize the number of heads that you get. So there are 10 coins in front of you. Each coin has some probability of showing heads. You get 1,000 attempts. You can toss the same coin 1,000 times. You can toss each coin 100 times. You can mix and match, like whichever strategy you want to play. The goal is to maximize the number of heads that you can get. This is called as the stochastic bandage problem because so the only feedback you get is whenever you take a coin, you flip it, you get to see whether you got a head or a tail today for that coin. So for any other coin, you get no feedback. Like the only way you can get a feedback on any coin is by picking it up and tossing. So if I give you like some 1,000 rounds, what strategy would you adopt to maximize the number of heads? Like in an ideal world, if I know the biases of all these coins, basically whichever coin has the highest probability, I'm going to toss the same coin 1,000 times. Compared to that, how well can I do? Like I, who does not know about the biases of these coins. And turns out you can get like some good bounds. Like you can get like again square root t kind of error. Some like square root t, square root n. Yeah. And the strategy is of the following kind. Like at any point, you've tossed every coin up to some accuracy. Like, sorry, you've tossed every coin like some k number of, like ki number of times. Based on that, so the point is like, okay, in general, you want to toss coins which have higher probabilities based on your past knowledge. But things could be like because of standard deviation and variance, some of the coins you've learned probably incorrect. Hence, you want to kind of do a careful trade-off between how accurately you've learned a coin and how much you're like, again, this exploration versus exploitation trade-off. So the UCB idea is something like the following, like come up with some kind of an upper envelope. I guess maybe let me use the envelope terminology, which we've already seen. So for each coin, come up with like some kind of an upper bound that you're guaranteed, like with very high probability, this coin's bias is certainly not above this. So suppose I've tossed a coin, like say 100 times, and it showed up heads like 50% of those, like let's say 50 of them. Then I know like I don't know exactly the probability, but it's going to be roughly around 0.5. And then maybe I can separately also argue with very high probability, it will not be more than 0.52. So come up with some kind of upper bounds on the probabilities of every coin. This is called as the stochastic bandage problem, and that's the algorithm. So basically the algorithm is on every coin, come up with some upper confidence and greedily then play. Basically, whichever coin has the highest upper confidence in every round, just play that coin. That algorithm you can show is kind of nearly optimal. And inspired from that, like that's the same kind of a trick that we'll be using here for these weakly monotone problems in semi-banded feedback. So the precise algorithm they do is the following. For each distribution, construct an upper envelope, di plus. And what is this di plus? It's nothing fancy. It's basically just look at the empirical distribution. Like I have, if NIT denotes the number of times I have received the sample from this distribution, you're kind of going to shift it up by 1 over square root n forward. Like, because this 1 over square root n is because like usually like after I've received k samples, there's plus minus square root k standard deviation. So to argue with high probability kind of a thing, you kind of move everything, whatever is the empirical mean, plus 1 over square root k or 1 over square root ni. So this is how you'll obtain these upper envelopes for every distribution. Send these upper envelope distributions to your stochastic optimization oracle, and just whatever algorithm it suggests, that's what you play. So this algorithm is literally inspired from UCB theorem or DKW inequality, like depending on what you find more intuitive. But yeah, so the idea is literally this. You have all these distributions. Although you don't know them exactly, in fact, you don't even have the same number of samples from each of them, I can get some kind of an upper envelopes on the performance of each distribution by just shifting the empirical distribution slightly up. And now play an algorithm which performs well for this upper envelope. The idea is the following. Either your upper envelope is going to be is actually the truth, in which case you're doing well. Because I'm like, actually, I learned like my empirical mean was 0.5, but the truth was actually 0.52. So this upper envelope is what I'm playing, so it's good. On the other hand, if it's not the accuracy, maybe the true mean was 0.48, because I'm now playing and I'm going to get another sample from this coin, it's going to make my accuracy even better. Like it's going to decrease this error band. And hence we are going to get like the best of both worlds in some sense. That's how the analysis goes. And yeah, so, okay, I'm almost out of time as well. The proof is not complicated. So the proof of this result is, again, as I was saying, You first argue because your distributions are discrete, this TV distance between the actual IR distribution and the upper envelope, that's small. So that's not very hard to prove because of these are discrete distributions. You can learn them even in TV distance. Uh, then you can argue that the regret in any round is basically sum up over all the IR distributions. Probability that your algorithm plays this ith random variable in this round times the TV distance. So this proof is not very complicated, but it's like a little subtle. So I'm not going to go over it. But basically, it roughly says is that there are two worlds. Either you play a coin or you don't play the coin, like a random variable. If you play it, then you're going to pay this error term, like whatever is the TV distance. But then this TV distance is going to go down in the future because you're going to get another sample from this coin, from this random variable. So basically, once you have this, you just like the proof is just 3 lines. Like the idea is basically the total regret is bounded by sum up. Like the intuition to keep in mind is the following. You have these n random variables. Each random variable, either you don't even play that coin, which means even if I look at its upper envelope, the most optimistic version of that ith distribution, that's also not good enough. So if I'm not playing it, then anyways, I'm fine because it's not a good random variable. There's no point in learning it more accurately. On the other hand, if I am playing it, I'm going to get more and more samples, and then my error is going down and down. So you can sum up, it turns out you get a summation of 1 over square root t. So the error kind of goes down. So this series gives you like a root t kind of a bar. Okay, so main takeaways from this part of the talk is that we've seen how online learning, what is online learning? How does it apply to all these stochastic problems, both for full feedback and partial feedback? The focus more was on partial feedback because full feedback is equivalent to pretty much offline learning. We saw how for banded feedback, you can get some t to the 2/3 kind of guarantees as long as I have access to like a sample from any particular distribution. I can get access to those. I have some algorithmic action that gives me that. For semi-banded feedback, we saw how we can get square root t regrets. Again, for all of these problems, one can do like for some of these problems or many of these problems, one can do even better. But we are covering mostly just general techniques that apply to very broad problems. But as I'm saying, like these problems are super important. So people in different communities, depending on like different communities care about different stochastic problems for that. So then they try to optimize and obtain like the best possible bounds for the specific problem. But these general techniques are already very powerful, and for very large classes of problems, they already are optimum. Uh, that's it. Yeah. Thank you. Any questions? Yeah. Thanks.